All right, let's go ahead and get started for the day here. So first I'm going to bring up the syllabus here. All right, so you should be seeing the syllabus. All right, so last week we went over the syllabus, and in the lab we watched a video about topographic maps, talked a little bit about topographic maps. Okay, so just want to reiterate that the syllabus quiz is due by the end of today, so if you haven't completed that, make sure you go in and get that done. Okay, also moving on to week 2, which is today, starts today. Okay, these are the things that you should have done before class today. Okay, so you should have read chapters 1 and 2 of the textbook. Okay, you should have completed the pre-lecture quizzes for chapters 1 and 2. And then also should have watched the videos 1 and 12 of the Earth Revealed series. Okay, so doing all that will prep you for lecture, and basically it's designed so that in lecture you'll have a pretty good understanding of the material, and that way if you don't, if you have questions or you're not understanding something, lecture is the time to ask those questions to ensure that you understand the material. Okay. All right, so before we get started with the lecture, are there any questions on anything? All right, not hearing anything. We'll just go ahead and jump in then. Oh, yeah, one thing I forgot to mention. So lab on last Thursday, I forgot to record it. So for those of you, if you need to go back and watch it, well, obviously you can't. Basically, we watched a topographic maps video, which isn't a big deal. We're going to actually, when we watch the pre-lab video here on Thursday, it'll go over a lot of those same questions. Let's see, we have a question. Lindsay, do you have a question?
Yeah, I do. I was wondering where in Blackboard do you upload the recordings?
All right, good question. So I think they've changed some things since the end of fall semester. So if you go to these 3 lines up here in the top left corner, click on that, you're going to see different pull downs because this is my view. But there should be one that says watch recordings or something of that nature. And then it'll bring up a list of the different recordings from the different days.
Okay, thank you.
So check that out. Yeah, if I'm wrong, by all means, shoot me an email and I'll take a closer look. But I believe that's how you get to it. All right, any other questions? Okay, all right, so as I mentioned on last Tuesday, during lecture, this is your time to ask questions if you don't understand anything. So don't hesitate to just come off mute and ask questions. Interrupting is perfectly fine, okay? that's part of the learning process. Yeah, I guess that's probably about it. So, well, let's go ahead and jump in. All right, so chapter 1's kind of an introduction to earth science, if you will. So we did briefly talk about what is earth science last Tuesday. So earth science is just kind of an amalgamation of these four separate science disciplines. So geology, oceanography, meteorology, and astronomy. So we'll spend the first half of the class going over geology. Okay, then we'll transition to, in the last half of the class, we'll cover oceanography, meteorology, and astronomy. All right, so first let's talk about some broad concepts. Okay, so when we talk about environment in this class, okay, what I'm referring to is our natural surroundings. Okay, keep in mind that when I say environmental, okay, this really is it focuses on the relationships between people and our natural environment, okay, because everything that we do affects the natural environment. Okay, so for any of you that have taken environmental science, you know that this relationship between people and the natural environment is very interconnected. Okay, we affect nature. Nature in some ways affects us, of course, things like natural disasters. Okay, also as we go through the class, you need to understand about the different types of resources. Okay, and chances are you guys already probably know this stuff, so I won't belabor the point. But there are two different categories of resources. You have renewable and non-renewable. So renewable, of course, these resources can be replenished. So think things like wind and water. Okay, plants, for instance, are renewable. A renewable resource. Then there are non-renewable resources. So these are resources that they're not necessarily not renewable, period, because they are. Okay, it's just that it takes a long, long time for these resources to be renewed. Okay, so think things like metals, fuel, so like oil products, petroleum, natural gas, things like that. Okay, these are resources that replenish at such a slow rate that there's no hope that they will be replenished, at least during our lifetimes, because as a general rule, they take hundreds of millions of years to replenish in the environment. Okay, so that's, as we go through class and we talk about renewable versus non-renewable, that's the difference. Okay, we're not necessarily going to, get too deep into the environmental science aspect of how people affect the environment, but we will. There are certain aspects where we will talk about that, especially with climate change. So, in order to do that, we need to have an understanding of how people how people affect the environment. Okay, so we know that the human population, if I recall correctly, is about 8 billion people present day. Population is rapidly growing. It's exponential. So it means it's not linear. It doesn't keep chugging along at a set rate, a very predictable rate per year. It actually, population grows to the point where more people are born each successive year than they were the year before. Okay? So as a result of the increasing human population, what we see is rapid use of minerals, energy, other natural resources, okay, both renewable and non-renewable. Okay, and as we get to the point where we have more and more people on the planet, we're going to start to see instances where even renewable resources are going to start to become in shorter supply. Okay, think water availability. We're already starting to see water availability start to result in interstate legal issues out west right now. Okay, those types of things are most likely only going to get worse over the coming years. Okay, also with the increase in human population comes the natural increased degradation of the natural environment. So the more people we have, the more resources we're using, which means that the more we're producing more waste products, we're polluting the environment more. So it's just a continued degradation of the natural environment. So they are interconnected, they're correlated. So it's important that you understand that these environmental issues, okay, they're not necessarily local, they're not necessarily global, okay? They happen at every level, okay? Environmental problems even occur at the household level, at the personal level, okay? We all are consumers in our economy. We all produce trash. We all use gas to drive to the store, to drive to school, whatever. Luckily, with the advent of internet classes and these VTM classes, we're doing a good part. We're trying to help out to save some of those resources, whereas we don't have to drive to campus to go to school, which is great because we don't have to burn gas to get there. So that's a plus. We're trying. So these problems aren't just specific to one area or one type of people, okay? It affects everybody, okay? So that is to say that these environmental issues, they're complex and they're often interdisciplinary, okay? So for those of you that might find yourself working in the environmental industry after you finish school, people like myself, you'll understand it a lot better that let's say you're a geologist, you're not going to be working with just geologists in the future. You're going to be working with an array of different other occupations, such as like engineers, biologists, mathematicians, social scientists, because all of the environmental issues are interdisciplinary. They're complex. It takes a whole group of different people to be able to really try to tackle these issues. So what are some of the human-induced environmental problems? Well, you're probably familiar with these already. So urban air pollution, of course, that's driven a lot by internal combustion vehicles. Acid rain, that's driven a lot by the burning of coal for power plants to produce electricity. Ozone depletion, actually not as big a deal as it used to be. We'll talk more about that in chapter 20. Climate change, of course, that's an issue that's near and dear to most of our hearts because we're starting to see changes that affect all of our lives beginning to repetitively occur, okay, and most likely will continue in the foreseeable future. So natural hazards, okay, are not human-induced, of course. These are things like earthquakes, landslides, volcanic eruptions, floods, etc. Okay, these are things that are going to happen regardless of whether people are around or not. It's just that when these do happen, you're going to see loss of life and loss of property, things like that. So natural disasters, of course, do affect us. And you'll see throughout the course as we talk, we see how natural hazards do affect our society a lot more, okay? All right, so I'll go ahead and stop there real quick. Are there any questions on anything before we move on to talk about something different? Okay. All right. So let's move on, talk about scientific inquiry. Okay, so science, all sciences, whether they're natural sciences, social sciences, they all assume that the world is consistent and predictable. And for the most part, I would agree with that, even though it seems like there's a lot of things that happen that are not predictable, okay, but they are definitely consistent, okay. We know that they're going to occur, we just may not know exactly when. So what are the goals of science? Okay, one is to discover patterns. Okay, that's probably the biggest one actually. We're just looking to see which things are related. Also, making predictions is a goal of science. Okay, and making predictions is done by testing and retesting what's called a hypothesis, okay, or predictions. So what is a hypothesis? Okay, at a most basic level, it's an explanation of something, an untested explanation of something rather. Okay, though in theory, and I shouldn't say in theory because that's just not correct to say. A hypothesis is you can test something that's already been explained because we know that in the natural world, changes do occasionally occur, such as climate change. So you can test things that have been tested, basically. Now, theory, okay? Theory is a well-tested and widely accepted hypothesis. Okay, so this is where a lot of people get kind of bent around the axles because these terms are kind of used interchangeably a lot of times, especially on TV. So you'll hear on shows, somebody will say, well, that's your theory. Well, what they really mean is, well, that's your hypothesis, okay? So at least you know now. Now every time you watch a movie or whatever, a show, you're going to be thinking that. That's what I do. I yell at the TV a lot when I hear that. It drives my wife nuts. But I digress here. So anyways, yes, a theory is well tested. So if somebody, is saying, here's what I think happened, it's actually a hypothesis. It's not a theory. So that is something that I'll ask you to keep in mind also as we go through this class, because I will talk about hypotheses and I will also talk about theories. Okay? And it's important that you understand the difference between the two, because when I say something is a hypothesis, I need you to know that it's something that's not well tested and widely accepted, but it's kind of currently something that's being talked about that's relatively new, okay, new to earth science. All right, so scientific inquiry is conducted via the scientific method, okay, and this is just simply a process whereby scientists will gather facts through observation, and then they'll formulate hypotheses which may eventually result in the formation of theories, okay? So what you're looking at here is the scientific method, just kind of broken down in a relatively easy to understand way. So let's quickly kind of go through this and I'll explain how it works. So we always start up here at the top with stating our problem. So let's say we want to know why is the sky blue? Okay. So we're going to go and gather information. That means we're going to go to the university library or wherever. You're going to do research. You're going to see what information is already out there that you can read and understand, so that you can help better understand the problem itself. Okay, so you're going to gather your information. After you do that, you're going to form a hypothesis, though often, quite frankly, most people typically are know enough about the subject already where they have already formed a hypothesis. But just that's just where it is in this whole sequence. Okay, so once you have a hypothesis formed and you've gathered information through existing research and literature, you're going to set up some sort of test. Okay, and that could be, the test could be through laboratory work, could be through field observations. It could also be in the form of literature reviews as well, if that happens. So you're going to test the hypothesis. Okay, as a result of that test, you're going to have a lot of data. Okay, so the next step is you're going to analyze that data. And then after that, you're going to draw conclusions based on what your data says. Okay, so down here at the bottom, so at the end of this whole method, you're going to come to one of these two conclusions. Was the hypothesis supported or was it not supported? Okay, and it doesn't matter either way. Okay, one is not better than the other. Okay, so a lot of times you'll kind of see a negative connotation that, you know, if your hypothesis isn't supported, that's a bad thing. Well, actually, no, it's not a bad thing, because what happens in that case is if your hypothesis isn't supported, as you can see here, you just go back to the form a hypothesis stage and you basically redo your experiment. You set it up differently, redo it, and then you do the experiment again and you draw, you get different data probably, you might draw different conclusions. Okay, this is how science works. Okay, you just keep repeating the process multiple times. Eventually, you may get to the point where your hypothesis is supported, but like I said, it doesn't matter. Okay, science evolves because people have gone through this hypothesis not supported repeatedly, trying to find the answer. Some people never find the answer. Other times it's a long time. Okay? If the hypothesis is supported, you still go back and repeat it a couple more times just to verify that it is correct. Okay. Any questions on the scientific method? All right. All right. So then we'll go ahead and move on. Start talking about actual earth science stuff, earth science specific. So here's what we're going to talk about with these different earth science disciplines. So the hydrosphere, okay, is an area on Earth that includes all of the world's water. Okay, hence the term hydro. Okay, so this includes the oceans, but it also includes fresh water that's found in lakes, streams, glaciers, and groundwater. Okay. One thing that I don't have in here that I just realized is, if I remember this correctly, since the atmosphere does have moisture that you can't see typically, the atmospheric moisture can also be part of the hydrosphere. Okay, but at the risk of confusing everybody, let's just maybe leave that separate for right now and just not worry about that. So hydrosphere, everything that includes water. Okay, the atmosphere, of course, is made of gases, and technically water vapor is a gas. You'll see that the atmosphere is made up of different types of gases, and I'll just leave it at that for right now, because we'll get into it in a lot greater detail. Okay, the geosphere includes all solid materials on Earth, okay, both on Earth's surface and within Earth itself. Okay, we're going to talk about this in greater detail here within the coming weeks, but there are three basic zones in Earth. Okay, the crust is the outer part that we live on. The mantle is the part below that, and then the Earth's core, of course, is in the middle of Earth. So each of these different zones have different compositional and chemical differences. Okay, so we'll talk about it later in greater detail. Then there's also the biosphere. We're not going to talk a whole lot about the biosphere because there's a whole class that talks about that, okay? And it's great. I love biology. We're just not going to cover a whole lot of that stuff in this class. But what we are going to do is we'll talk about biology as it applies to earth science, because as we saw before, all the sciences are interconnected. We can't talk about earth science without talking about some biological concepts, because we know there are biological things that affect the Earth system, such as plants respiring moisture into the atmosphere. Okay, so there's one linkage. So technically, the biospheres, everything from the bottom of the ocean floor really up into the atmosphere, you know, where birds fly. But as we all know, most life is on Earth's surface. Okay, so Earth's structure, getting back to the geology part, so the crust is the britter outer shell. Let me see here. So here's Earth's broken down into those three layers that I talked about. The crust is this very thin, kind of brownish gray layer here that you're seeing at the top. That's where we live, of course. That's this part right here. When we break this uppermost part away, you can see that this is the crust here. Below that is the mantle. That's this red area. Okay, and then of course in the middle is the inner and outer core. Okay. Okay, then there's also the couple of vagaries. Let me talk about those real quick too. So the lithosphere includes both the crust and a little bit of rocky material right below the crust. Okay, so I don't know why geologists felt the need to kind of separate those two out, but for all purposes of this class, you can just assume that lithosphere and crust are the same thing, so that you don't get, you know, too awful confused. Okay. Also in the mantle here, there's a part in the upper mantle. Okay, so this is the mantle here. There's a part in the upper mantle which is this darker red area. That's called the asthenosphere. Okay. This is a very important layer in Earth, that it's important that you understand what happens in this layer and why those things happen. It's very important, especially with plate tectonics, as we go to talk about that. Okay, but basically this asthenosphere, it's considered to be a solid but mobile medium. Okay, and I know that sounds contradictory. The way I like to describe the asthenosphere is a lot like hardened putty, where if you press hard enough on hardened putty, you can actually get it to deform, okay, even though it is technically hardened. The asthenosphere is pretty much like that, where it's made of rock that's so hot that it's close to melting, okay? And because it's close to melting, that means it's starting to get a little bit of kind of a malleable, smashable consistency to it. Okay, and basically it's this layer, the asthenosphere, in which Earth's tectonic plates ride on top of. Okay, so I'll leave it at that, and we'll return to that in greater detail. Actually, I think in chapter 3, we'll talk all about that. So the core I already talked about. Compositionally, the core is made of metals, okay, whereas the crust and the mantle are made predominantly of rocky materials with some metals. But it's important to know that the core is made of basically nickel and iron for the most part. There's some other minor metals in there as well. The outer core is a liquid, whereas the inner core is a solid. Okay, and the reason why this occurs is because of pressure, certain changes in pressure. So we know that at the area where the outer core is, there's enough pressure at that specific area where these metals are actually compressed enough where they go from a solid to a liquid state. Okay, but then you keep going and you add even more pressure in the inner core, and that liquid state actually goes back to a solid state. Okay, so it's a very interesting thing that happens there. Okay, plate tectonics. So plate tectonics is one of the most important concepts in earth science. Okay, so this it's basically a theory that says Earth has a bunch of plates on the lithosphere, or the crust, that rest on top of that mobile asthenosphere layer. Okay, and they move in relation to each other. Okay, and it's that movement that causes a lot of causes a lot of geological processes. Let's put it that way. Okay. All right, so any questions on Earth's structure before we move on to a different topic? Okay. All right, so what are some sources of energy? Okay, the sun, of course, is basically a nuclear reactor. Okay, nuclear fusion in the sun, which basically is decay of radioactive materials, creates one of the things it does create is heat. Okay, among other things, and that heat is discharged from the sun into outer space, where it makes it to Earth, goes through our atmosphere, and basically it's Earth's surface, heats up Earth's surface. Okay, so the sun is the #1 provider of energy on Earth, but in addition to just providing heat, the sun also drives a lot of Earth processes, including the weather, ocean circulation, and then erosion processes. Okay, so we'll go into those all later and talk specifically, and you'll see exactly how the sun does drive those processes. The moon. Okay, the moon also the moon doesn't provide energy like the sun does in the way that you would think it does, as in heat. It doesn't provide heat. But what it does is it provides a pull that affects water in the oceans. So tides are caused by the gravitational attraction of the moon. Okay? And as Earth rotates, we know that tides go up and down in the oceans because as the Earth rotates, certain areas are closer to the moon, certain areas are further away from the moon. Thus, the amount of attraction is consistently changing throughout the course of one day. Okay, so we'll talk about the tides later on as well. Earth's interior is the #2 provider of heat energy. Okay, so just like the sun, radioactive decay is occurring within Earth's core, and so this radioactive decay is creating an immense amount of heat that basically moves outward from the core up to Earth's surface. And once that heat reaches Earth's surface, it's the main reason that we experience a lot of natural disasters and Earth processes, because what happens is this heat is what drives the plate tectonic cycle. And so we know that plate tectonics is responsible for earthquakes, volcanoes, and mountain building. So that's why I say, you know, plate tectonics is something that we're going to talk about here next week that's super important. And you'll better understand that plate tectonics is responsible for a lot of the earth processes that happen. All right. All right, so let's move on and talk about systems here, earth systems. So a system is just a group of interacting parts that creates a whole, okay? There's open and closed systems. Okay, open systems are where energy and matter flow into and out of the system freely. Okay, an example is weather. We know that weather, basically you can have, you know, changes in temperature, you can have changes in moisture content, you have energy moving here and there. So the system is, every energy and matter is moving around, okay? There's no boundaries except for Earth's atmosphere, the top of the atmosphere. Closed systems are different because they're closed, they're self-contained. That means energy and matter cannot flow into or out of the system, okay? Do we have a question here? Okay. Grace, what did you need me to go back to? The open systems, okay. Oh, and here I am doing this without the thing in presentation mode. I'm losing my mind. Okay, so you can see here you have light energy coming from the sun onto Earth, okay? And you also have heat energy that's being what's called re-radiated from Earth's surface out from Earth into outer space, okay? So the system, as you can see, is open. There's no boundaries to the system. You can have energy coming in and out. Okay. Now with closed systems, these are a little more complex because they are self-contained. So as I said, energy and matter cannot flow into or out of the system. So think of this as your car, okay? You have a coolant system that connects the engine block, the radiator, the heating system, the heating core, I believe it is. And I'm sure there's other parts that, since I'm not an expert in automotive stuff, but basically you have pipes that they move your antifreeze around through these different components, but that antifreeze never leaves those pipes. It's consistently flowing through the different components, but it doesn't leak out unless you have a leak, okay? With a closed system, it's assumed you don't have a leak, okay? So when we're talking about, you know, using the car as an example of a closed system, it's assumed there's no leak, okay? So the antifreeze, you don't have to worry about checking the level because nothing leaks, nothing burns off. It's always the same amount. It just keeps going in a big old circle. Okay, so the water cycle, also known as the hydrological cycle, is one of the most predominant closed systems on Earth, okay? And by that, I mean, we have a set amount of water on Earth, okay? And that amount of water hasn't changed in about 1 billion years, okay? What initially brought water to Earth, it's thought to be a combination of the materials that were already present when Earth was formed, as well as some comet probably brought some moisture that crashed onto Earth. But anyways, those things, nothing has changed for about the past 1 billion years. So what we're seeing on Earth now in terms of water quantity is the same that it has been for a long time. It's just that this water cycles through different reservoirs that you can see. So for instance, the atmosphere, ocean water, lakes, running water called streams, glaciers, okay? And within plants, because we know plants contain a lot of water as well, okay? So water is just moving, constantly moving between these different reservoirs, basically. Okay, any questions on the systems, open or closed? Okay. All right. And we will move on and talk about the formation of Earth and our solar system in general. Okay. So the origin of Earth is described in the nebular theory. Okay. And it's a theory because it's been widely tested and accepted. So basically, it all started with what's called the Big Bang. Okay. The Big Bang is where basically there was something created from nothing. Okay. And I don't want to get too deep into this concept because I know it seems elusive. But basically, the reason why they say something was created from nothing was because it was basically a supernova explosion. So what you had was, at the time, only energy was present. Okay. When the supernova explosion occurred, energy was turned into matter, or the things that we see now, the actual physical things like rocks. So that's what they mean when they say something from nothing. So you had the Big Bang about 13 billion years ago. Okay, over time, what happened was the matter that was created continued to synthesize, continued to basically change over time based on changing conditions. And so initially, the early universe was made up of the lightest gases like helium and hydrogen. Over time, you saw chemical changes occur within those gases to become, well, to create some denser material, such as oxygen, which is a more dense gas. And then also of course, later on, all of the material, all the matter that we see presently. Okay, so that nebula, a nebula began to form about 5 billion years ago. Okay, and a nebula is just simply a flat disk-like accumulation of matter that's spinning in a circle. Okay, that's what B is here. So Big Bang over here. This is the formation of our nebula. Okay, so as you have this material spinning in a circle, what's happening is it's all beginning to condense together with the material that surrounds it. So eventually, what you start to see is this nebula turns into a situation where you have rings of matter that have clumped together, and then you have matter that's drawn into the very center of the swirling mass to create a very dense, hot mass, which of course is the sun. Okay, so over time, what you get is these rings continue to coalesce. The matter coalesces more together, and it eventually creates individual planets with the material. Okay, and those planets continue to move around that central star, the sun, over time, just like you're seeing here, all this matter that's segregated into rings. Okay, while we're talking about segregation here, okay, how the inner planets form versus the outer planets is different. Okay, we're going to get into that in greater detail when we go talk about astronomy, but just right now, I'll let you know that as as this segregation began to occur in rings and the planets began to form, the the denser matter, so the rocky material, stayed closer, whereas the less dense material, so the ices and the gases, for the most part, they were shoved out to the outer parts. So these outer rings, and those created the outer planets, or what we call the gas giants. Okay, so that's why you see the difference between the two different types of planets, the terrestrial or rocky planets that are the inner ones. Then you have the gaseous outer planets. Okay, so that's a look at basically how Earth formed in the earliest days. Okay, so then we get to the concept of differentiation. So we're at a point now where those rings of material have clumped together into basically big balls that are now individual planets. Okay, so that's where we're at in the formation of Earth's stage. So at this point, Earth is still very young. It's very hot, okay, because there hasn't been enough time for anything to cool down yet. And so that means that at this point, everything is still in a molten state. Okay, it's a liquid. But what this liquid is made out of is everything we see on Earth today. Okay, so you have liquid metals, you have liquid rocks, you have water vapor, you have all these other gases as well in a vapor state. It's all mixed together. Okay, but as time goes on, Earth begins to cool down. Okay, as it cools down, you start to see these different materials of different densities begin to separate out. Okay, so you have the less dense materials rise up towards the surface. The more dense materials, like the metals, begin to sink down toward the core. So over a long period of time, you get the very dense materials in the core. The very light materials get sent out towards Earth's surface. So the gases and the more non-metals, rocky type material. So it's important to understand that heat is what drives the differentiation process, or what drove it, okay? Now, we already kind of talked about it, but it's worth reiterating here. So basically what drove the differentiation process, at least on Earth? Well, it was kind of two things. One, it was the heat left over from when the universe was created, okay? So Earth was slowly cooling down. But as differentiation progressed, okay, what ended up happening was the metals went down to the core, and some of those metals had radioactive materials, so like uranium, for instance. And those radioactive materials underwent nuclear fusion, which they currently still do. And that nuclear fusion is what created a lot of heat, which drove differentiation. Okay. Also, high velocity impacts by debris, solar system debris, so like comets, basically, meteorites. You get these big rocky materials that crash into Earth's surface and causes an explosion, okay, and a lot of heat. So we know that high velocity impacts also played a role in differentiation as well. Also, it's worth noting that as differentiation began to occur, like I said, the lighter materials began to go out towards Earth's surface. Okay? And the gases, specifically, over time began to collect and create a primitive atmosphere. Okay? Earth has actually had a couple different atmospheres over time, but we'll talk more about that later. Okay. So are there any questions on chapter 1 here before we move on to chapter 2? Lindsay, you have a question?
So this was a little earlier on, but I was wondering if, so you said that natural hazards aren't caused by human beings, but I was wondering if climate change causes them to happen more frequently.
Yes and no. Yeah, as I said, it's very complex. I guess I don't want to spend a whole lot of time talking about that specific example. We'll go over it when we talk about climate change. But basically, yes, humans are changing the Earth system, which ultimately results in changes to climate. So I think that's maybe like a quick answer, and I'll put a bookmark in there until we talk specifically about climate change. Any other questions? Okay. All right, well, let's go ahead and take a 5-minute break before we start chapter 2. So 3, 4, 5, 6, 7, 8. Let's say 10:59. We will resume back here and we will cover chapter 2. All right. Let's go ahead and jump back into our lecture. Okay, so now we're going to move on to chapter 2. And I do ask that, if I'm not accidentally not running the PowerPoint in presentation mode, this is not presentation mode. This is. So if I forget to do that, by all means, somebody come off mute and let me know. That way it's easier for everybody to see. Okay. There's going to be a lot of pictures that I use in these PowerPoints, so it's pretty important that the presentation be as big as possible. All right, so let's talk about minerals. Okay, so minerals. First thing I want you to understand is that minerals and rocks are not the same thing. Okay, so minerals are defined by a handful of different characteristics. Okay, and what you're seeing is those characteristics are right here. So they have to be naturally occurring, so they cannot be man-made. Okay, so like a cubic zirconia, which is a man-made diamond, that isn't considered a mineral. Okay, but a natural diamond is. It has to be solid, so it can't be liquid. Has to have an orderly crystalline structure. So from a chemistry viewpoint, it has to be the same shape, basically. Okay. Has to have a well-defined chemical composition. Okay. Again, going back to chemistry, it has to have the same chemical formula. Okay. If it's a diamond, that means it has. If you have two diamonds sitting in front of you, that means they have the same exact chemical composition. They have the same exact shape. Okay. They have to be, let me go back. They're generally inorganic. There are a couple examples of minerals where they are actually organic. And organic means basically that they contain living material, okay? Carbon material. Okay. So an example of a mineral that is organic is called amber. That's tree sap. As we go to look at fossils, there's actually, you can get, if you go on the internet, you can see examples too of ancient creatures like spiders, mosquitoes, whatever, that fly into tree sap, and that tree sap hardens with that insect in it. And basically, because it cuts off all the oxygen, the tree sap cuts out all the oxygen when it solidifies, means decomposition or rotting can't occur. Okay, so that's one example of inorganic, organic rather. Otherwise, most minerals are inorganic. They're not made of organic material, carbon material. A mineral must also be represented by a specific chemical formula. And the most important part is that a mineral is not a rock. Okay, so as we go over this chapter and the next chapter, you'll see the difference between minerals and rocks, but I'll give you a spoiler alert right now. Rocks are made of minerals. That's how it works, okay? So before we go into talk specifically about minerals from a geological viewpoint, you need to understand a little bit of chemistry, real basic stuff. And for a lot of you, this will probably be just kind of a refresher. So I won't belabor the point. I'll move through it quickly. If you have any questions, or if you want me to go back and talk more specifically about something, by all means, let me know. So an atom is the smallest particle of matter that cannot be chemically split. Okay, so everything that is in our natural world, everything from your body to the computer sitting in front of you to your glass of water, really all gets broken down into a tiny particle called the atom. Okay, and that atom since it can't be split, That's the smallest that you can break it down. Okay, so an atom, here's a picture of an atom here. Okay, it gets broken down into what's called a nucleus. That's kind of a central area where you have these protons and neutrons located. Okay, protons have a positive electrical charge. Okay, and the protons are shown here as these red circles. Okay, neutrons, which are shown in blue, they have a neutral electric charge. Okay, and in the next couple slides, I'll explain what these protons and neutrons do. Okay, then you also have a electron, which are these basically little balls that are zooming around the nucleus in all sorts of different directions. Okay, so these electrons have an electric charge. Okay, and these electrons, they form in layers. Okay, called shells. Okay, and at the very outside layer, or the very outside shell, is called the valence electrons. Okay, and it's these valence electrons that alter, basically at a most basic level, they bond with other atoms. Okay, so you have other atoms that also have valence electrons on the outside edges. It's the valence electrons between the two different atoms that attract to each other to connect together, basically. All right, so any questions about atoms, the kind of the structure of atoms? Okay. Just so you know, we'll get into it in a lot greater detail later on. These numbers, which represent the different protons and different neutrons, those can change, okay? And there are implications in Earth science based on when those numbers change, but I won't get into that right now, okay? But I'm going to kind of briefly explain it, but I'm not going to go into really great detail until later on. So basically, when you clump a bunch of atoms together, you create an element. Okay, an element is atoms of the same material. Okay, so for instance, if I want to make oxygen, I take oxygen is O2. I want to take 2 atoms of oxygen. Okay, put them together. That creates the element oxygen. Then we have a molecule, which is 2 or more atoms of the same element. I'm sorry, I always do that. The element itself is would just be like the O. Okay, just one single atom. The molecule is when you start to add multiple atoms together. Okay, so like O2. As you can see, a lot of this is just vagarity. It's a lot of it's just terminology. The terminology is just very specific. It's just important that you understand how these things work, not necessarily the specific terminology. So a compound is a molecule that contains one or more of one element or the other. Okay, so basically, when you start to add, let's use water as an example, H2O. Okay, that even better, hydrogen peroxide, H2O2. So what you have is chemically combined is 2 atoms of hydrogen that are already bonded together will bond with 2 atoms of oxygen that are already bonded together. Okay, so when you take different elements and start bonding them together, okay, that's when you start to create compounds. And compounds, you'll know when something's a compound because it contains different elements with multiple atoms attached. Okay, so like C6H12O6. Okay, that is going to be a petroleum derivative. That would be considered a compound because it's kind of like alphabet soup in a lot of ways. Okay. All right, so the atomic number is the number of protons in the atom's nucleus. Okay. The mass number is when you add the number of neutrons plus the protons. So basically, you take all these circles found in the nucleus, you add them all together, that's the mass number. Okay, the atomic number is just the number of protons, which is the red ones. Okay. And how that kind of works out, how it becomes useful to us, is in the form of ions and isotopes. So ions are atoms that gain or lose electrons. Okay. So when you have chemical bonding, in this case, what we have here is sodium. We have these valence electrons on the outside, in the outside shells of each of them. They're going to join together. Okay. In that process, they may lose or gain an electron, depending on what kind of chemical reaction is occurring. Okay, so that's called ionic. Okay, I'll give examples while we're going through class of ions and isotopes. Okay, then there's isotopes. Okay, this is where you have the nucleus. In the nucleus, there's varying number of neutrons. Okay, and because different number of neutrons, that ultimately affects the mass of that specific compound. Okay, for element. Okay, so one example of how this applies to earth science is with what's called carbon dating, radioactive dating using different carbon isotopes. So we have carbon-12, carbon-13, carbon-14. Okay, carbon-12 is your run-of-the-mill standard carbon. It has 6 protons, 6 neutrons. Okay, that's found in a plentiful amount on Earth. Okay, what can happen sometimes is you can gain a neutron, okay, while the number of protons stays the same. Okay, so when you gain a neutron, then it becomes carbon-13. You're just adding one number to it. That species of carbon is found in quite a bit less quantity as the carbon-12. Same thing with carbon-14. You're just adding 2 neutrons, okay, and thus its number goes up 2 from 12 to 14. So how does this, what implication does this have for earth science? Well, mainly with fossils. Okay, when we get to it, I'll explain it in greater detail. But basically, when we're radioactively dating materials to figure out how old something ancient is, what we're going to do is we're going to compare the number of these different isotopes. Okay, we're going to see how many 12 isotopes there are, how many 13, and how many 14 there are. We're going to compare that based on what we know from that environment during that specific time in the past. Okay, so I'm going to put a bookmark in that for right now, and just know that isotopes are used for radioactive dating. Okay, and then we'll pick it back up when we get to it. All right, are there any questions about structure of the atom or ions and isotopes? Okay. All right, so then let's talk bonding here. So there's 2 different types of bonds, ionic and covalent. Okay, this is where the valence electrons come in. So with a ionic bond, you have the valence electron in the outer shell get transferred from one atom to another during the bonding process. You basically get two atoms that come together, such as sodium and chloride. They come together, you get basically the transfer of a valence electron from the sodium to the chloride. Okay, now with ionic bonds, the ultimate bond itself structurally is a lot weaker. Okay, so things that tend to have ionic bonds, okay, think like table salt, for instance. You can smash up chunks of salt pretty easily. Okay, there's also a lot of earth material that is also ionic. That means that it's easy to break it up, to split it. Okay, then you get covalent bonds. Okay, this is where when you have two different atoms coming together to bond, the valence electrons, rather than one moving from one atom to the other, the valence electrons come together and they bond. So they basically join together. And this results in the formation of a much stronger bond than an ionic bond. So the very hard minerals out there that are present on Earth, such as diamonds, those are covalent bonds. Okay. For ionic bonds, think of something like talcum powder, which is actually baby powder. That actually comes from a mineral called talc. Talc has an ionic bond, and as a result, you can just crush talc with just in your hand. But you know that you can't crush a diamond in your hand. That's because of that covalent bond. Any questions about these two different bond types? Okay. All right. So that's kind of a chemistry primer as we go to talk specifically about minerals. So minerals basically are categorized by different what's called physical properties. Okay, you're seeing those properties here. We're going to go through and talk about these individually next. Okay, so first is luster. This is how a mineral appears when light is reflected off of it. You basically have two different possibilities. One is metallic, the other is non-metallic. When light reflects off of a metallic luster, it looks shiny like this, okay? When light reflects off of a non-metallic mineral, it looks dull, aka not shiny, okay? Non-metallic can really be broken down into different kind of subcategories. So non-metallic minerals, or well, rather minerals that have a non-metallic luster, they can look kind of glassy, they can look oily, they can look kind of dull in appearance, and then there's more as well, but I won't go on. So as you basically tell is that the main way to separate luster out is by shiny versus not shiny. Okay, so this here is galena, the mineral galena. Okay, it is metallic, so it is shiny. But what you're seeing here over here is also an example of galena. Why is it not shiny? It's because it's been oxidized in the environment. So the environment over a long time has basically degraded the surface of the mineral to where it doesn't look shiny anymore. You basically have weathered material on the surface. So if you were to break this chunk up and look at the portions that have never been exposed to the atmosphere, it would be shiny. So the inside would be shiny. So when we're looking at minerals, sometimes it's confusing because you'll be looking at a piece of galena that may not appear to be metallic because it's not shiny. But we have to remember that the environment, basically over time, the environment causes anything to start to basically rot, to degrade, okay? Okay, habit is just a shape, the shape of the mineral. Okay, and I'm also going to use the term crystal interchangeably with mineral. Okay, just know that there's different types of habits. Okay, probably the more common ones are bladed, which are kind of flat, elongated strips. Blocky. Okay, this mineral here is blocky. This is called pyrite or fool's gold. Then you have banded. Banded is basically when you have layering. Okay, so tabular is book shaped. So yeah, just a bunch of different ways, different shapes that a mineral can appear. Okay, color. Color can be a good way to tell some minerals, but as a general rule, color is not a very good way to diagnose, to identify minerals. And I say that because there are some minerals that can come in multiple colors. So what you're seeing here is 4 samples of the mineral quartz. Okay, quartz is basically pure silica. Okay, and in its normal form, pure silica is colorless, or as you might want to call it white, but geologists refer to the color that appears white as colorless. Okay, so what might cause these colors? Impurities. So you have maybe some metals over time that have leached within the crystals, and that think iron, for instance. Maybe iron has leached into a sample and then it's oxidized to create rust. And so you have a reddish orangish color of quartz. Okay. Same thing with these other different colors. There's impurities, different other elements that are found within the chemical structure that have just changed its color. So be careful when you're looking at color as a diagnostic tool. But for some minerals, like quartz, olivine, for instance, which is a mineral that's found in the rock below the Earth's oceans, color is a good indicator because it's either going to be greenish or yellowish in color. So it's kind of a hodgepodge, but definitely don't rely on color. Okay, streak. This is when you take a white ceramic plate, okay, and you take the mineral itself and you just rub it across that plate, the streak plate. What will happen is most often you'll see a colored streak, okay, and what that means is that whatever mineral that is, as you're rubbing it against that hard streak plate, it's breaking off little tiny pieces of that mineral and leaving them behind in the form of the streak. Okay, but what's kind of interesting is there's some examples of minerals where the streak color is different than the outward appearing color of the mineral. So what you might say is kind of a brownish colored mineral may actually have a brown streak, a black streak, okay? And one example is pyrite, which again is fool's gold. We already saw that one here. This is pyrite in its normal form, which is metallic, as you can see. But if you look here at this sample, it looks completely different, okay? It's because this sample has been oxidized. It's been exposed to the environment, so it's not in its pristine condition. So yeah, streak can be a good identification tool. Now, in the instance where you get a mineral that is harder than this streak plate, when you streak that mineral across the streak plate, it'll actually the mineral will scratch the streak plate, okay? So that brings me to this next property called hardness. So when I go to use streak as an indicator, I use it in conjunction with hardness. Okay, so I'm basically testing the two at once, kind of. So I'm going to use a streak plate as a hardness indicator because I know that a streak plate is a 6.5 out of 10 on this hardness scale, which is called the Mohs scale. Okay. So in the Mohs scale, we have the very weak bonded minerals with the ionic bonds, like talc and gypsum. They're lower on the scale, so 1, 2, 3. The very hard, durable covalent bond minerals are higher on the scale, 8s, 9s, 10s. So think diamond, for instance. That's the hardest known natural material. That's a 10. So a streak plate has a 6.5 hardness. And then as you can see, there's also some of these other common things that you'll find around the house or around your lab that you can use to test the hardness of a mineral. So for instance, fingernail at a 2.5. If you go to scratch your fingernail against a mineral, if your fingernail scratches that mineral, we know that that mineral is less than 2.5 because your fingernail scratches it. If the mineral scratches your fingernail, then you know that the mineral is higher than 2.5. Okay, so you can use a penny, a wire, a piece of glass, okay, and a streak plate. You can also use other minerals that you have already identified for sure, and you know what they are. You can use them because you already, if you've identified them, you know what its hardness is. So let's say I tried to streak a piece of talc against a diamond. Okay, well, I know what their hardnesses are, so I know that the talc is going to get destroyed by the diamond. So these are just different ways that you can test the hardness. Okay, so and like I said, streak plate is one of them. All right. I think that's it. All right, cleavage is another property that can be used. Okay, the key term here is cleave. To cleave, it means to break along a plane of weak bonding. So somebody's got their has your you're not muted. Sorry. Can everybody check to make sure that you're muted, please? I don't, like I said, I don't have an issue. I really want you guys to come off mute and ask questions and whatnot, but I do ask that if you're not doing that, keep your mute on so that we don't pick up any background noise. Again, I have enough background noise on my side already. Hopefully it's not too annoying. Thank you for getting that muted. So even just to break apart along a plane of weak bonding, usually that plane of weak bonding is an ionic bond. Okay, so those the weak bonds that we talked about for the softer minerals like talc, if you take a knife and slice across a piece of talc, it'll easily cut. Okay, and that's what's called a cleavage plane. Okay, I think that's pretty self-explanatory. So here's examples of common cleavage planes in minerals. This column here is the number of cleavage directions. That means when you look at a sample, how many cleavage planes does it have? Okay, how many different ones? For some, it's going to be one. That means it basically looks like sliced potatoes or whatever, like just look like you just slice the mineral into, you put it through like one of those food processors, right? Okay, So an example of that is called a mineral called muscovite. It looks very sheet-like. Okay, then you can get two cleavage planes, and this is where we start to kind of differentiate, because with minerals that have two cleavage planes and three cleavage planes, those get further subdivided at the angle at which the cleavage occurs. So we have minerals that will cleave at two different angles, well, two different places rather, two different directions, but those directions are not at 90 degrees to each other. And then there are minerals where those two cleavage planes are at 90 degrees to each other. So let's look at those two examples. An instance where we have two cleavage planes that meet at 90-degree angle, that's feldspar. Okay, we have a cleavage plane here, a nice flat cut. Then we have a nice cleavage plane right here. Okay, and they meet at 90 degrees. Okay. If we go down here to this mineral called hornblende, which sometimes is found in the rock granite, you'll see that there's a cleavage plane here and there's one here, but they don't meet at 90 degrees. They actually meet at an angle that's bigger than 90 degrees. Okay, so you're just seeing the differences in angles, that's all. So this looks more like a parallelogram, whereas when they meet at 90 degrees, they look more like a box or a rectangle type situation. Okay. All right, so that is minerals that have two cleavage planes. Minerals that have three cleavage planes, think of those as boxes, okay? Because the top and then the two sides are all cleavage planes, okay? So think, for minerals that have three cleavage planes, think, the way I look at it is think height, width, depth. When you go to measure the volume of something, right? You measure those three variables. Think of those three variables as your three cleavage planes. You have the depth, height, and the width. So just like we saw with the minerals that have two cleavage planes, the ones that have three cleavage planes, those cleavage planes can either meet at 90 degrees or they can meet at an angle that's different than 90 degrees. So this mineral halite, which gets crushed up and turned into table salt, notice it looks like a box. Okay, it looks boxy. That's three at 90 degrees, three cleavage planes at 90 degrees. This mineral down here looks kind of like a tilted box or parallelogram. That's the mineral calcite, which makes up predominantly the mineral, the rock limestone. You can see that the cleavage planes do not meet at 90 degrees, okay? So hopefully that description kind of helps you understand how cleavage planes works and how different minerals can be differentiated based on whether or not cleavage planes meet at 90 degrees or not at 90 degrees, okay? Another example is four cleavage planes, okay? This is basically, these take on the appearance of like two pyramids stacked up against each other, okay? Or you might just call it like a prism shape. But basically the mineral fluorite takes on this shape, okay? Okay, all right, are there any questions on the cleavage? Because this is probably one of the more difficult to understand properties. Let's see here. Okay, good. Lower. All right. So no questions. Okay, the next physical property is called tenacity. And that is basically the ability of a person to deform it without breaking. So that mineral that has that one cleavage plane that we just looked at called muscovite, you can actually, with two hands, you can grab both sides and you can bend it, okay? That bending is called tenacity. How far can you bend it before it breaks? That's its tenacity. So there's different types. It can be brittle, where it'll break pretty much right away when you put any type of pressure on it. That's pretty common for a lot of minerals. Malleable or ductile, this is common with metals, where let's take you take a hammer to it. Take a hammer to gold, for instance. Gold is a very malleable element, and it's easy to reshape, hence why it's been used for jewelry for thousands of years. Basically, malleable means to just, it'll reshape when pressure is applied to it. Okay, sectile, layers can be separated with a knife. Okay, that's examples of minerals that are sectile tend to be minerals that have that one cleavage plane, like. Okay, then there's elastic. Elastic is interesting. It's the ability to bend without breaking. Okay, now muscovite is also elastic. Okay, I know it seems kind of weird that it can be two, but with muscovite, yeah, you can bend the two edges, and as long as you don't put so much pressure on it that it breaks, it will, if you let go, it'll go back to its original shape. Okay, so that's called elastic. Typically, minerals that are sectile are also elastic. Okay, that's usually how it works. Okay, other mineral properties. So here's some of the more interesting ones. So fracture, that's when you take a hammer to it, okay, and depending on how it breaks will determine whether it's fracture or not. So when you take your hammer to it and it breaks, if it breaks up into just a bunch of individual shards of different shapes, then it's fracture, okay? That means is that the mineral doesn't have cleavage. There are actually minerals that don't have cleavage. If you take a hammer to any mineral that does have cleavage, as long as the mineral is weaker than the hammer, when it breaks, the mineral will actually break into individual little pieces that all exhibit the same cleavage. So let's say with halite, the cubic looking mineral that salt is made from, if you smash it with a hammer, it will break up into many, many little cubes that look exactly like the one it was before you took the hammer to it. Okay, quartz on the other hand, quartz, which is a very durable mineral that's found in granite, when you take a hammer to it, quartz will break up and fracture. It will break into many different pieces that are typically jagged and shaped differently. Okay, you might also know of quartz as glass, because that's essentially what it is. Okay, glass is made from the same stuff that quartz is, basically tiny little silica grains that are all cemented together. Okay, so you know how glass is when it breaks. It's fracture. So quartz is the same way. Okay, also there's taste. So in the lab, I always like to joke about this one because I don't want anybody licking samples of minerals to test taste. So I give that property away for the minerals where taste applies. Anyway, density. So how heavy is it? Is it real heavy like a metal, or is it really light like a silica-based rock? Okay. or talc, for instance. Smell. Does it smell like rotten eggs? Because that's a clear indicator that it's the mineral. It's a mineral that contains sulfur. There are several of them. Okay, and sulfur, by the way, is gas that you smell coming out of the ground at Yellowstone. It smells like rotten eggs. Okay, that's sulfur. Okay, sulfur as hydrogen sulfide. So smell. Some minerals smell like rotten eggs. Just a handful of them. Feel. How do they feel? Or is it rough? Is it smooth, jagged, etc., etc.? Magnetism. There's a couple minerals that are actually magnetic because they contain a substantial amount of iron. Okay, magnetite is an example. Okay, hence the term magnet. Magnetite is most often you can get a magnet to attract to it. It really depends on how much iron is in it. Okay, then there's double refraction. This one is really interesting. It's too bad, we aren't physically in lab to be able to see this, but what you see, this example here is double refraction. So calcite is a good example of double refraction. This is where when you look through it, you can actually see double. So if you put, a sheet of paper down with some words on it, you'll actually see two sets of the words. Okay, that's because of the refractive properties within that mineral. As you're looking through it, the refraction breaks up that word into two separate viewings. That's even a word to describe it, I guess. It makes it so that you're seeing that word twice. That's because of the refraction. Okay, then a very useful one as well is called is any mineral that has a reaction to acid, to any acid for that fact. Typically, we would use very, very dilute, about 10% hydrochloric acid mixed with 90% water in the lab, and we would drop it on certain minerals. Okay, there are certain minerals that are made of basic materials. Okay, and by basic I mean pH scale, basic and acidic, right? So we know that when we mix acids and bases, bad things happen, right? Okay, well, that same bad thing does happen, just not on a grand scale. So when we mix, or when we have rocks or minerals that are made of basic materials such as calcite, okay, when we drop the acid on it, what you get is a chemical reaction. You get the dissolution of the basic material, and that emanates as bubbles, okay, which is also called effervescence. So if you get effervescence on that mineral, you know that it's most likely a mineral like calcite or one of its very close cousins. So that's a good diagnostic tool to use. Are there any questions on any of the mineral properties that we talked about? Okay. All right. So now let's talk about how minerals are composed. So what you're looking at is the 8 most common rock-forming mineral elements, essentially. So the 8 mineral-forming elements. Oxygen and silicon are the biggies, hence most rocks are what's called silicates, which are made of oxygen and silicon. But when you break it all down, yes, this is kind of the general composition of all the rocks we'll ever find on Earth. All right, so let's start to break them apart into different groupings. So first we have silicates. Again, silicates are the most common grouping because of silicon and oxygen being most of the building materials. So these are made up of oxygen and silicon atoms, okay, bound together. What you get is the little tiny blue silicon, one tiny blue silicon atom is wedged in between 4 of these oxygen molecule, individual O2 molecules. And so the appearance looks like a pyramid, which is also called a tetrahedra. Okay? So silicates always appear in this tetrahedra shape. So when we look at different types of silicates, really what we're doing is breaking them down based on how many chains of these tetrahedra there are. Okay, so in the first category, we have just a single tetrahedra. That means just one of the tetrahedra, just one pyramid. Okay, so one of these right here, all by itself. That's the mineral olivine. Makes up a good amount of the ocean floor. Okay, then we have single chains, which is right here. Okay, that's also referred to as the pyroxene group. Okay, so you have individual tetrahedra that are all joined together to form one single long chain. Okay, then as you can imagine, we get into double chains here, which is two chains added together. And then lastly, sheets. Well, not lastly, sheets, which is just when there's more than one, more than a double chain. So basically 3 or more chains put together. Okay. Then we get what's called a three-dimensional network. Yeah, I'll cover it in a couple slides, but three-dimensional network is basically just a hodgepodge, basically taking a whole bunch of these individual tetrahedra and gluing them together in all sorts of weird shapes. So some examples of that are the mineral quartz and the mineral potassium feldspar, both of which are the most common minerals found in the rock granite. Okay. So micas, such as muscovite, that mineral that is sectile, that you can bend a little bit, and it'll move back to how it was. That is sheet-like. Okay, and hence it means you can basically cut across that one cleavage plane to make a sheet-like appearance, which is exactly what you're seeing here. Okay, feldspars, again with that 3D network. Basically, there are two cleavage planes at 90 degrees in this instance. I know it doesn't look like it with this specific picture. It looks like they're not at 90 degrees, but they are. It's because of the way the picture is angled. So feldspars, the feldspar group of silicates is the most abundant group of minerals on Earth's crust. Hence, granite, rock granite, is probably the most prominent rock that you'll find on Earth. Okay, so that is the silicates. Now we're going to move on to the non-silicates. So everything else that is not made of oxygen and silicate. Okay, so here's the examples right here. We're going to look individually. We're going to look individually at these ones. So first we have the carbonates. Okay, these are also known as calcium carbonates. Okay, these they contain the molecule CO3 carbonate. Okay, and this is pretty typical for minerals like calcite and its cousins, dolomite and aragonite, which are pretty much the same thing, except that they have magnesium, a little bit of magnesium in their chemical formula, whereas calcite has no magnesium. It just has calcium carbonate. So calcium plus CO3. Okay, so these are the minerals that will effervesce when you drop acid on them because they are made up of basic material. The carbonate compound is very basic. Okay, halides are materials that are formed by evaporation. They're also known as evaporites. Okay, basically think desert. When you're in a basin area that gets occasionally flooded by thunderstorms, the water will rush down there, and then within a couple days, the water has evaporated, but it has left crusty white salts. Okay, those are evaporites. They're a mineral that the water has been evaporated, and then only the mineral material is left behind. So halite and gypsum are examples of halites. Okay, sulfides, they contain the S2 molecule. Okay, these are the ones that smell like rotten eggs. Okay, since they contain sulfur. Galena and pyrite. Okay, generally they're not going to smell. These two aren't going to smell horribly like sulfur. There are some better examples that will, but if you smell it, galena, pyrite, or the others, you will smell at least a scent of rotten eggs. So why not? Why not go smell those rotten eggs? That's a good diagnostic tool. All right, sulfates. Sulfates contain the sulfate ion. That's SO4. Anhydrite, gypsum. These form very similarly as the evaporites, where basically they form as a result of evaporation. Okay, oxides, they contain the O2 molecule. So these tend to be the minerals that also contain metal deposits, which is kind of interesting. So oxides are often the minerals that will attract a magnet if you hold it over it, such as magnetite here. Hematite, sometimes hematite will do it, but not always, depending on how much iron it has. So also the mineral corundum, which is a very hard mineral. It's high up on the hardness scale. It's an oxide, and you probably know corundum better as the gemstones, ruby and sapphire. Okay, so real quick, what's the difference between gemstone and mineral? Well, technically, if they're both natural, they're the same exact thing, compositionally, shape-wise. It's just that a gem has been fancied up with, it's been polished, shaped to look all nice and neat. Okay, so a gem is just a fancy looking mineral that's been humanized. Okay, then there's native elements. These are just all the metals that we see around the world. Okay. I will point out that, as I said, that some metal deposits are associated with oxides. Okay. The difference between an oxide and a native element is that with oxides, the concentration of metals is going to be a lot lower because there's a higher concentration of O2. Whereas with native elements, these are typically just straight metals. There's nothing else found within those minerals. No O2, just the metals themselves. Okay. All right, so we're getting close here to the end of the presentation, so hang with me. We should be done here very soon. So mineral resources. Okay, these are occurrences of useful minerals that will eventually be extracted for use. Okay, so this just means that if you have a mineral, a company that owns mineral rights means they own the rocks below the land that contain the metals, but they haven't been mined yet. Okay, that's the setting that we're talking about here. Okay, so mineral resources are occurrences of minerals that could be extracted. Ore deposits are concentrations of, they're high concentrations of metallic minerals that are kind of clumped together within a rock that can be mined for a profit. Mineral resources typically means the metals aren't all segregated together like you see with ore deposits, but they could still be mined to make profit, but it's just going to cost more money to separate the rock from the metal. Whereas an ore deposit, typically there's a lot less work associated with it. Okay. So that's kind of how the mining of metals works. Okay, guess that was it. Oh, there was maybe another slide after that. All right, so what I'll do is I will take the time now to see if anybody has any questions on anything that we talked about today. So chapters 1 and 2. All right, hearing nothing. So let's talk about Thursday. So our first lab. So we're going to do lab number 7. So you just need to show up to class on Thursday at 10. Also go into the labs folder and have lab 7 downloaded, as well as the topographic map that's also in the same folder. Okay, you'll need that to be able to use that to answer some of the questions in the lab. Okay, other than that, that's it for today. So we'll go ahead and conclude. You guys have a nice and safe Wednesday with all the snow, and stay safe. We will reconvene on Thursday from the snowy safety of your own house. So have fun. Take care. See you on Thursday.
Bye. Thank you. Take care.
Thank
Bye.
you.
Thank you.
Thank you.
Bye. Thank you.